so now let me we formally defined what is a DFA, right? We saw all this Q, sigma, delta, Q0 and S. So basically this is the Q is the set of states which is finite, sigma is the set of alphabet which is finite, delta is the set of, delta is a transition function, in other words which are the arrows. So if the alphabet is binary, if it is 0 1, then every state will have 2 outgoing arrows. So for here, for instance, S has 2 outgoing arrows, one for 0, one for 1. Q1 has 2 outgoing arrows, one for 0, one for 1. So in this case, one of these outgoing arrows comes back to Q1, which is okay. And in some cases, some of these things could be combined. Like over here, we have the outgoing arrow for 0 and 1 both come back to Q2, right? So delta is a transition function. Q0 is a starting state, which is only a single state, one state, and F is the set of accepting states, which are denoted by this double circle, right? So denoted by this. Now let us formally define when a string is accepted. We have already understood this. This is just a formalization of the same. So we say that a machine or a DFA M accepts a string W. So W is a string, okay, and W1, W2 are the individual symbols in it. So let's say if W is, let's say, 1011, then it is like W1 is 1, W2 is 0, W3 is 1 and W4 is 1. So these are the 4 individual symbols. So this is just W broken up into symbols. So we say that a machine M or a DFA M accepts a string. Basically, if this string, upon moving as per the string, you end at an accepting state. So in other words, basically there is a sequence of states such that R0 up to Rn. So R0 is the state before you read anything, and R0 has to be the starting state, and the first symbol W1 will take you from R0 to R1. So and W2 will take you from R1 to R2. So this is just formalized here. The I plus 1 symbol will take you from Ri to Ri plus 1, right? So where the I plus 1 goes from 1 to n, or in other words, I goes from 0 to n minus 1. And finally, you end at the state Rn, which has to be an accepting state, which is what is listed here. So in other words, what is going on is the machine starts at the starting state and moves as per the rules and ends at an accepting state. So it's fairly simple. It's just a formalization of whatever we have seen. So we say a DFA accepts a string if at the end of processing that string it ends at an accepting state. And what do I mean by processing? You start at the starting state, and then each symbol you make the correct move. Okay, and we say M accepts a string, and correspondingly we say the machine or the DFA M recognizes the language A, right, where A is the set of all strings that are accepted by the DFA M. Okay, so I have been kind of alternatively using machine and DFA, but I'll continue to do that. So think of machine, DFA as the same computing device. So the distinction here is that M accepts a string and M recognizes a language. Okay, sometimes people say M accepts the language, but that can lead to a bit of confusion. So that's why we are trying to use M recognizes the language A. So M recognizes the language means A is a set of all strings that are accepted by M. It is exactly the set of all strings. So A is not a superset of the strings, or it's not that A is a subset of the strings. A contains if a certain string is accepted by M, it has to be in A. If certain string is not accepted, it should not be in A. It's exactly those set of strings that are accepted, right? Not a subset or not a superset. Sometimes we also denote it by this notation: L of M is equal to A. Okay. So now let's see another example. Let's try to construct a DFA that accepts all the binary strings which has the number of ones in those binary strings are divisible by 5. Right? If you count the number of ones, it should be divisible by 5. So let's try to see how to make use of the states. So recall, we have only a finite number of states. We only have a finite number of states, and we want to use that, right? So here the DFA needs to keep track of the number of ones. So need to keep track the number of ones, but we don't need to keep track the number of zeros. That's okay. But then there is a problem, like let's say if the string is huge and it has 100 ones, so you need to keep track of the number 100. So number 100 has to be is a multiple of 5. So do you keep counting? If so, there is no limit, right? So how do you keep track of that much? The answer to that is that we don't need to keep track of the exact count. We only need to keep track of the count modulo 5. So we don't need to keep track of the exact count. We only need to keep track of the count, the modulo 5. In other words, the count, the remainder of the count when divided by 5. So, so the key idea here is this, that so we need to have a set of states. So the thing to keep track should be the number of ones. So basically we can have something like this: Q0, Q1, Q2. I'm sorry, I think I have a Q1, Q2, Q3, and Q4, and so trying to keep track of the number of ones that you have seen. So Q0, if you see a 0, you remain there. If you see a 1, you move to Q1. So which means you have seen 1, 1. If you see a 0, you remain here. If you see a 1 here, and same thing you keep repeating. And what happens when you see a 1 at Q4? So which means again it's like we have seen 5 ones. So now it is like we just need to keep track of the count of ones modulo 5. So if you see 5 ones, it's the same as 0 ones. So you can come back to Q0. So now I have 5 states, and for each state I have 2 outgoing arrows. The thing that is missing is which are the strings that are accepted. So as the picture is currently, no string is accepted, right? So the strings that have to be accepted are those strings after after which you, like, in which there are the number of ones is number of ones is divisible by 5 or is a multiple of 5. So let's just try some examples. So let's just think of the string 1 1 1 1 1. So you start at Q0, 1 1 1 1 1. You can end at Q0. So this has to be accepted. So let us mark Q0 as accepting, right? And what if the string is 1 1 1 1 1 0. So it is the same movement, and then you remain it at q0. So this is also getting accepted. And now you can kind of play around with this and see that any string that is desired indeed gets accepted, right? So this is the way to construct a DFA. So basically we need to figure out what is the information that we are trying to preserve, because we only have a finite set of states and we need to keep track of what is the information that we need to keep track. So I have a question here in red color. Set of all binary strings where the number of ones is 2 modulo 5. Okay. So here the number of ones was a multiple of 5. So now we are saying 2 modulo 5. What is the DFA that gives us this language? So if you think about it, the same kind of counting mechanism still works, but the accepting state may have to change. So maybe I won't give away the answer now, but you can think, can we reuse the same structure but changing something small? Just think about it. Okay. And now we come to the another definition. So notice that I am using these numbers here, so this is the definition regular languages. I am using these kind of numbers. These are just the numbers that are there in my edition of CIPSR, which is the second edition, I think maybe international edition, second edition, but I am just using that to keep track. If you have a copy of the textbook, which is Michael CIPSR, that may not have the same numbering, but I will try to keep it consistent within my course or this course. Right? So we say that a language is regular if there is some DFA that recognizes this. Right? So this is a definition. So all the languages that we have seen so far, set of all strings that have where the number of ones is divisible by 5 is a regular language because we drew a DFA for it. And these languages, set of strings that start and end with the same symbol, that is a regular language. Set of strings that end in 0 is a regular language, strings that end in 1 is a regular language, and so on, right? So regular language is a language is regular if some finite automaton recognizes this. So let's just see some more simple examples for construction. So a DFA for the following, where the alphabet is A B, not 0 1, where the string contains A B as a substring. Okay, so the input must contain A B as a substring. So if at any point of the string A B appears, so A B B must be accepted, B B A must not be accepted, B B must be accepted because there is an AB here, right? A must also be accepted because there is an AB there. Right, let's see. So let's try to draw a DFA. So we have a starting state, and let's see what happens. We have a starting state. Now we need to, for seeing an AB substring, we first have to get an A. So if there is a B from the starting position, we can remain in the same state. Okay. And if you see an A, you move to the next state. And after seeing an A, you could still keep seeing A. So for instance, like BBAA. So that you may be here. So, but once you see an A, now you are halfway there. You have seen A. Now you just need to, if either you keep seeing A followed by A followed by A followed by A and so on, or at some point a B will appear. So whenever the first B appears, that will result in an AB substring. So when the first B appears, you can accept, you can lead to an acceptance, because now whatever comes after this, right? So either you may see an A or you may see a B. Now whatever comes, it doesn't matter, now you can accept, because you already seen AB as a substring. So now you can see what is going on here. This DFA indeed captures this, all the strings that have AB as a substring. You can work out and see what happens. So one exercise is, what are the strings that you can try out at home, is what are the strings that end in the first state. Let's say this is Q1. What are the strings that end in the second state, and what are the strings that end in the third state? We know what are the strings that end in the third state. These are the strings that contain AB as a substring, right? Because it's a single accepting state. But try to see what are the strings that end in the first or the second. Now let's try to look at another question which seems very related. DFA for the set of all AB strings where W does not contain AB as a substring. So it's exactly the opposite of what we are seeing now. So how can we not contain AB as a substring? So as I said earlier, once you see an A, you cannot have a B later, right? Because once you see an A, either you keep seeing A, or if you see a B, then you have a substring AB. So this is not possible. So once you see an A, you have to only be seeing A's, right? But you could see B's prior to the A, right? You could see B prior to the A's, but you cannot have A's prior to the B, because then again it's an AB. So the only two things possible are strings of the form B, 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 like a full of B's, or in other words it's like B star, or it could be of the form some number of B's followed by some number of A's, which is like B star, A star. So these are the only set of strings that should be accepted. And if you notice, which is kind of what we did right over here. So you have a state Q1 where till you are stuck here if you keep seeing B's. If you see an A, you move to Q2, and then you remain there if you keep seeing A's. If you see a B again, you move to Q3, sorry. And then you are stuck at Q3. So Q3 is a set of strings where AB features as a substring. Q1 and Q2 are, so Q2 is you have seen at least one A. Q1 is you have only seen B's, right? So all B stars end in Q1. Once you see one A, you move to Q2, right? And otherwise you move to Q3, and then you can check that this DFA indeed accepts all the strings that does not contain AB as a substring. And now you can see one interesting thing, though I reasoned it slightly differently. These two DFAs, the one over here and the one over here, they are kind of the same DFA. Right? The transitions are exactly the same. It is just that the accept states are different. So in fact, the set of accepting state of the second DFA, let's call this is M1 and let's call this M2. The set of accept states of M2 are the opposite of the accepting states of M1. Right? So M1 and M2 are kind of complement in that sense. And the language also, interestingly, what we were looking for is the complement. So here in the case of M1, we were looking at for all the strings that contain AB as a substring. M2 recognizes all the strings that do not contain AB as a substring, right? So M1 and M2 are complementary, and this gives us the following statement, that regular languages are closed under complement. Because you can have the same construction of the DFA, just that whatever is accepted by the, let's say you, so what does the statement mean? Maybe I'll just explain about it for a minute. Suppose there is a language A which is regular, then the language A complement, which is all the strings that are not in A, that is also regular. This is what it means. So A is regular if and only if A complement is regular. So what I want to say is that if A is regular, then A complement is also regular. Why is this true? Suppose A is regular, then there is a finite automaton for A, right? So maybe some states, some transitions, let's say, right? So let's say the red ones are accepting and the blue ones are not accepting, right? Now this is the machine that accepts A. Now to get A complement, right, you could have exactly the same thing, but with the blue ones accepting and the red ones not accepting. So any string that ended in red will now not be accepted, and any string that did not end in red will be accepted. So something like this is, it's not it's only a pictorial thing. Right? So all the blues are accepting and all the reds are not accepting. So this will be a complement. So take any regular language, there is a DFA for it. Now you take the same DFA, you make accepting as not accepting, and you take the not accepting as accepting. So you take the set of accepting states and you take the complement of that will give you the DFA for a complement. So this is what we are saying, is that this is what it means to say regular languages are closed under complement. If A is regular, a complement is also regular, right? I have in between, I have one more question here that you can try. Set of all binary strings where the string ends in begins with 1 and ends in 0. So try to construct this as well. So I'll just this is the end of the lecture, so I'll just summarize what we have seen so far. So we saw what is a finite automata, we saw some examples of a deterministic finite automata, or DFAs as we called it. It is deterministic because each state has exactly one outgoing arrow for each symbol that we see over there, and it is finite because there are only finite number of states. So the language of a DFA is the set of strings that are accepted by the DFA, right? And we formally saw the definition. The definition is a 5-tuple with a number of states, alphabet, transition function, starting state and accepting states. We saw some examples about some DFAs and which language they accept, right? We formally define what it means for a machine to or a DFA to accept a string, even though we had informally seen that. We say that DFA M recognizes the language A if A is a set of all strings that are accepted by M. Then we saw some languages for like some questions of this form where we are given a certain language and we wanted to create a DFA for it. And we defined regular languages, which are the set of all languages for which we can construct a DFA. Right. So one may ask at this point, like, why do I make a definition like this? It may seem to you that for anything you can make a DFA. All languages you may be able to make a DFA, but that is not the case. At some point we will see why that is the case, right? Maybe not at some point, very soon. So these are a special class of languages for which we can make DFAs, right? Not all languages, we cannot make DFAs for all languages. And then we said that if A is regular, meaning if we can draw a DFA for A, we can also draw a DFA for A complement. In fact, it's the same DFA, but just that we change the accepting state to non-accepting and non-accepting state to accepting, just like what we did over here, right? So accepting to non-accepting and non-accepting to accepting, right? And so that's a summary of this today's lecture. And in the next lecture, that will be lecture 4, we are going to see regular operations. Okay, so these are union, concatenation and star operations, and we are going to also after that we are going to explore closure under regular operations. So closure under regular operations means, so union is an operation where we take two languages and take their union, set union, okay, and concatenation and star we will define in the next class. So we want to say things like if A is regular and B is regular, and then A union B is regular, meaning that if there is a DFA for A and a DFA for B, we can build a DFA for the union of A and B, and similar statements for concatenation and star, right? So this is that's all for the lecture on regular languages, and see you in the next lecture.